This video picks up the last topic from Chapter 2, the definition of a sentence for SL. In English, some words go together to make sentences, and some just don't. We rely on intuition and rules of grammar to tell the difference, but there are times when it's hard to tell. Even if you're a linguist, sorting every string of English words into sentences and non-sentences is really hard. In SL, however, we can formally and precisely define what counts as a sentence. This, for example, is a sentence of SL, and that's something we'll show by the end of this video. Recall that we specified all the symbols of SL. They include sentence letters, connectives, and parentheses. An expression of SL is any series of these symbols. Some expressions of SL count as well-formed formulas. Well-formed formula is typically abbreviated WFF, and that's sometimes pronounced woof, sometimes it's just pronounced WFF. Every sentence letter is a well-formed formula. That includes all the letters A, B, C, down through Z, but also remember we can add subscripts. So we get A1, J6, P3, Q2, and whatever else. Point being, all of those are well-formed formulas, and there are infinitely many of them. Suppose we have an expression that's a well-formed formula. Then we can make another well-formed formula by adding a negation to the front of it. So we know P on its own is a well-formed formula because it's a sentence letter. That means we can make not P, which is also a well-formed formula. We can make not P. You might be worried about the grammar of double negatives, but even in English, double negatives are not impossible. And because of this rule in SL, that if you have a well-formed formula, you can make another one by adding a negation to it, this just follows that rule. Not P, clearly a well-formed formula. And we can continue making not P, and so on. We could add negations to the front until the cows come home. Now suppose we have two expressions. Both of them are well-formed formulas. If so, you can make a new well-formed formula by putting a conjunction between them and parentheses around the whole thing. So that gives us well-formed formulas like A and P. We can do that again to get A and P and Q3. Now if you have two well-formed formulas, you can also make a new one by putting the disjunction between them. So that gives us things like M or N. And applying the rule again, M or N or P. And again, if we have two expressions that are well-formed formulas, you can make a new one by putting an arrow between them and parentheses around the whole thing. So we get things like P1, arrow P2. And applying it again, Q, arrow, P1, arrow, P2. And of course, we can do the same thing with the biconditional. If you have two well-formed formulas, which could be atomic sentences, or they could themselves be long, complex, compound things, you can put a parentheses around them and a biconditional between them, and you make a new well-formed formula. So you get things like S if and only if R, and S if and only if R, if and only if S, if and only if R. An expression of SL is a well-formed formula if and only if it can be built by repeated applications of these rules. This turns our rules into a definition because it captures all the well-formed formulas and only the well-formed formulas. Recall that a sentence, in the sense we're interested in, is a bit of language that has a truth value. In SL, the atomic formulas are atomic sentences, so they have truth values. The sentence letters all have truth values. And all of the connectives are truth functional. So if the things we connect have truth values, the compound formula does too. That means that the rules we have, which define what counts as a well-formed formula, will always give us something that has a truth value. That means that an expression of SL is a sentence if and only if it's a well-formed formula. It may be roundabout to offer two definitions, but things aren't always going to be so easy. For QL, the logical language we'll be looking at later, there are well-formed formulas that aren't sentences. You might have noticed also that the definition never adds parentheses with a negation. Doing so simply isn't allowed. So P is a sentence, not P, not P. But not parenthesis, not P, close parenthesis, is not a sentence because our definition of a well-formed formula doesn't let parentheses get added when you're just putting a negation on the front. However, our definition, all the rules we were looking at earlier, adds parentheses for every two-place connective, for all of the other connectives. So this is a sentence, even if it is hard to read. We're going to add some notational conventions to make things like this easier to read. You can use square brackets as parentheses. The square brackets are just a different way of writing parentheses. They aren't a new symbol of SL, but they let us write the sentence in a way that's easier to see where the opening parentheses match up with closing ones. So we can rewrite that sentence at the top so that it looks like the thing at the bottom. Also, you can leave off the parentheses around an entire sentence. If we want to put a negation in front or fit this together with some other formulas, we'll need to write down those parentheses. But around the whole sentence, we know they're there even if we don't write them down. Note also that the rules only allow you to put together well-formed formulas with conjunction if you have two parts. And so that means if you're symbolizing A and B and C, you'd have to decide between these two possible ways of doing it. However, in English, we don't ordinarily do that. We have lists of things where we just use and we don't distinguish how they would go together in pairs. So, as a notational convention, we'll say that you can leave out parentheses when there's a serial conjunction. That is, a series of this and that and that. The rule says you need a parenthesis to make around every pair of things, but you can leave it out. For purposes where it matters, you can add the parentheses back, and the two sentences at the top are equivalent, so you could just use either one. In a similar way, A or B or C, strictly speaking, requires that they be bracketed off in pairs, but you can leave out the parentheses in a serial disjunction. So we're adopting a convention that says a sort of like informal rule that says you can write the thing at the bottom, and we can understand it as meaning one of the two at the top. Note that you can't do this with a conditional or biconditional. To summarize, we've got four notational conventions. We have a precise definition of a well-formed formula of SL, which also defines a sentence of SL. And these extra notational conventions are ways that we make our lives easier. You can use square brackets rather than parentheses anywhere as a substitution. You can leave off parentheses if they're around an entire sentence. You can leave out parentheses in a serial conjunction, a series of ands. And you can leave out parentheses in a serial disjunction, a series of ors. So let's go back to this monster. I said it was a sentence of SL, but how can we tell? Well, it's a sentence if we can build it up using our rules. How could we have put this together? Well, we have two parts stuck together with a biconditional. So by the rule, the whole thing is a well-formed formula if the two parts are. But how can we tell about them? Start on the left-hand side. It's built from two parts stuck together with an or. So it's a well-formed formula if both of the parts are. On the left-hand side of this disjunction, we've got this conditional. It's a well-formed formula if both the antecedent and the consequent are well-formed formulas. And here we bottom out in sentence letters. Both sides of the conditional are sentence letters, and those are well-formed formulas just on their own. We jump back up to consider the right-hand disjunct? It's a negation, and that means it's a well-formed formula if what follows the negation is a well-formed formula. So that's this bit, which is a conditional. It's a well-formed formula if both the antecedent and consequent are. Again, we've bottomed out in sentence letters. Now we look at the right-hand side of the original biconditional. It's a disjunction. And that's going to be a well-formed formula if both sides, both disjuncts, are well-formed formulas. And those are just sentence letters. We can visualize this as a tree. Starting with the smallest pieces, sentence letters, we combine them using the various rules that appear in the definition of a well-formed formula to make compound parts. And once we've made the compounds, we stick those together, either with other atomic sentences or with other compounds, to make more and more complicated pieces until we can fit together the whole thing. The connective that you look at first if you're taking this sentence apart is the biconditional. Put the other way, if you're building this sentence up from pieces, the last connective you put in, the last connection you make, is here at the biconditional. So for this sentence, the biconditional is the main logical operator of the sentence. That means at some level of description, it's really an if and only if sentence. There's something on the left-hand side, if and only if the thing on the right-hand side. This sentence is a biconditional because its main logical operator is a biconditional. Of course, each of the sides have their own symbols and their own sentence letters and their own complicated structure. One way to use this definition is to note that only a sentence of SL can be a correct answer when you're translating. So for last week's homework, if you entered something that wasn't even a sentence, it couldn't even possibly be a right answer because it's ungrammatical. Of course, you could enter the wrong sentence, but if you've entered something that isn't a sentence, it's not even a candidate to be a right answer. For what we're starting this week, the structure of sentences is going to be crucial for truth tables. A truth table involves setting values for the sentence letters and working through the branches of the tree, calculating the value at each step until we've determined a value for the whole sentence. We'll get into that soon, but it builds on the fact that the truth value of a sentence, built with one of the connectives, is a function of the truth value of its parts. We'll say more about that in the next video.